Before we do that, again, this part, today's lecture is going to be the last lecture for chapter 2. So we will do a quick summary in what we covered after these two sections, right? So remember, in chapter 2, we discussed the first law of thermodynamics. We did a review on classical mechanics. What is PV work? What is heat? And then we also discussed the definition of heat capacities, Cp and Cv. And then we introduced a Joule experiment and Joule-Thomson experiment so that chemists can build a link between internal energy or enthalpy with something we experimentally measure, like the change of temperature with respect to volume or change of temperature with respect to pressure. So at the end of our last lecture, we went in and discussed a little bit in how do we apply the first law of thermodynamics to ideal gases. So today we're gonna finish that discussion in looking at two special scenarios. Namely, the first scenario we're gonna look at is the isothermal expansion of gases. All right, so this part is not gonna focusing on ideal gas, it's generally true, but later on we'll see the special application of the isothermal expansion of ideal gases. So, first of all, the question I ask you at the end of our last lecture is, well, how do we know what is the heat flow for an isothermal process? All right, or do we know anything about the heat flow of an isothermal process? So the whole point of this discussion here is try to break the link of heat and temperature change. One of the common misunderstanding in thermodynamics is that, well, when there is no temperature change, people are too quick to jump into say, hey, no temperature change, so heat equals to 0. So that's simply not true, right? We see an application in our last lecture when we were saying, well, in last week, I don't remember which lecture it is, right? Remember, you can stir that cup of water to get the temperature up and then have the heat transfer to be a negative number later on, right? So this one is the more general application to say, like, now let's just look at an isothermal expansion of gas or an isothermal contraction of gas and see how exactly heat is transferred. So in this process, we can think about setting up this question as, say, our initial state is, say, V initial, P initial, and some temperature T. And then what we want in our final state is that V final, P final, and again, some temperature T. And in here, let's focus on the isothermal expansion first. The contraction works the same way. Let's set our V final to be larger than V initial. All right. So this process, that's what we call an isothermal process because the temperature is kept the same. So when we're talking about heat and work, remember we want to define specific path. So we know how they actually are, so we can actually calculate the change of heat and work. So let's do that. Let's say we have a hypothetical path. Say between my initial state and my final state, we have a hypothetical state. Now the difference between my initial state and my hypothetical state is an expansion of volume. So we have V final. And then our pressure is going to change with it. And let's manually set this process to be an adiabatic process. And a reversible adiabatic process. Reversible adiabatic. Right, so that's the first step. We're having a reversible adiabatic expansion of the gas between your initial volume to the final volume. Now, in this process, since it's adiabatic, my system is doing work on the surrounding. My temperature must change, right? But let's take this step to be a very small one. So the change in my temperature is a super small one, like an infinitesimal change in temperature. Of course, my pressure is also going to change alongside with it. And then my second step will be the difference between my hypothetical state to my final state. All right. And in this process of your hypothetical state to the final state, we're keeping our volume to be fixed. And my temperature go back to what we want, to the set temperature that we have. So in this process, what exactly is happening? Now, this is generally true, right? We don't have an equation of state. So let's simplify ourselves to ideal gases and see for ideal gases, what exactly is the relationship between your volume change and your the heat transfer in the process, and how do we derive it using the first law of thermodynamics? So in this process, since we're assuming ideal gas, there are a few things we can write down whenever we assume a system is ideal gas. Say we have PV equals nRT. We have internal energy is only a function of temperature. Enthalpy is only a function of temperature. My CV and CP are constant. All right. And in this case, what do we have? In our first step, we have an adiabatic process. So we know that for any adiabatic process, my heat equals to 0. Or Q1 equals to 0 for the first adiabatic process. We also know for the first process, we have an expansion, a reversible expansion, in which my system is doing work on the surrounding. So we have W1 equals to integral of negative PdV from V initial to V final. And since we know PV equals nRT, we can write it out as V initial, V final, negative nR over nRT over V dV. All right. So in this case, my temperature is also changing, but since our temperature change is like very small, we can treat it as like a constant ticket.
Why do you have two negatives?
Yes, sorry. So since our temperature is super small, we're talking about only a very infinitesimal change of temperature, because ideally it should be an isothermal process without any change in temperature. So in this process, we're taking that T out to have negative nRT, and V initial, V final, 1 over V dV. Or effectively, we can write it out as negative nRT line V initial over V final over V initial. So that's our first process, right? And our delta U of my first process equals to Q1 plus W1 equals to, well, W1, which is negative, nRT line V final over V initial. So that's our first hypothetical adiabatic reversible state, expansion of the gas. Secondly, we have that movement between our hypothetical state to our final state, in which we kept our volume as fixed. Now your pressure and temperature can change in that process. Now, in our second step, we're keeping volume fixed, and since we're only looking at PV work, and for volume that's fixed, our work must equal to 0. So my W2 equals to 0. All right. And, well, something else we need. We know that as a final, like 1 plus 2, our total internal energy change for my ideal gas must equal to 0 because it's isothermal. My internal energy only depends on temperature. So the total delta U must equals to 0, and this equals to like delta U1 plus delta U2. All right. So using the relationship of the total internal energy change must equal to 0, we can go back to here to say my delta U2 equals to negative of delta U1 equals to nRT line V final over V initial. So we have this first, and then we use this relationship to go back to our second step. All right, for my second step, we didn't say adiabatic, and we know that my delta U2 equals to W2 plus Q2. My first Q is 0. My Q2 thus equals to my delta U2, which is the nRT times ln V final over V initial. And the overall heat equals to Q1 plus Q2, which is nRT times ln V final over V initial. Yes?
How did you create a hypothetical state?
Well, you don't necessarily need to. It's just like to help you understand a path that can take place. Okay, any other questions before we go on? Or the other way to put it is whenever we're talking about an isothermal expansion of the gas, just keep in mind temperature that's more directly related to our internal energy change, especially when we're talking about the ideal gases, right? So my internal energy, U, is a direct function of temperature, but heat is not. Heat is defined by specific path in which the process is taking place. So no temperature change doesn't mean heat equals to 0. That's a take-home message for this application here. Any questions? No? Okay. Let's move on to our second part. This one is also interactive, means like we're gonna work on it together. First of all, we'll read the problem together and see like if to make sure we're on the same page. So how do we read a problem and set up our calculation? So in this question, we're giving you a specific process, which is a reversible adiabatic process of a perfect gas or of an ideal gas. What we want is to solve for a relationship between temperature and volume for this process. All right. And in here, when reading the problem, when you see reversible, what we have is write down the dW reversible equals to negative PdV. Secondly, adiabatic, you write down dQ equals to 0. And perfect gas or ideal gas, we write out PV equals nRT, U as a function of T, H as a function of T, CV and CP are constant. And now the question becomes, using the first law of thermodynamics, can you derive a general relationship between temperature and volume for any reversible adiabatic process of an ideal gas? Right, so again, in thermodynamics, we have lots of jargons, like as we were talking about adiabatic, reversible, ideal gas. So knowing like how to translate these terminologies into equations that helps you solve the problem, that's something you want to get very, very familiar with. So let's try this together. And I hope you can work it on your own piece of sheet and I'll work it on the board, or we'll discuss later on in how do we solve this problem. All right, so I hope you can get this expression from just writing down the general form of the first law of thermodynamics. So the du equals to dw plus dq, that's the general form of the first law of thermodynamics. And then we're just writing out each term and see what they are by using our conditions, right? So dq equals to 0 because in our condition, we say this is an adiabatic process. That's why q is 0. We say this is reversible, so dw equals to negative pdv, and since it's ideal gas, the pressure is expressed as nRT over V, and then for du, we have Cv times dt because it's an ideal gas, right? So just this part is simply translating whatever in the problem into equations we can eventually solve. And from here, what we can see, on the left-hand side, we have differential of temperature. On the right-hand side, we have differential of volume. So what we want to do is moving the terms, so temperature go with temperature, volume go with volume. And in this case, let me just move the temperature to the left. We have Cv over T dt equals to negative nR over V dV. Right? Then what we can do? We can take integral on both ends, since we have, on the left we only have temperature, on the right we only have volume. So taking the integral, let's take the constant out, so Cv 1 over T dt equals to negative nR 1 over V dV. Right, so that's an indefinite integral we can solve by referring back to the table. And they are very straightforward integrals that you can solve. So solving this integral, we get Cv ln, ln t, and then if we're looking at two different states, 1 and 2, that's T2 over T1. On the right, we have negative nR ln V2 over V1. All right. And then we can just moving these constant inside to my logarithm. just to try to get that logarithm out, what we get is ln, well, T2 over T1 to the CV equals to ln V1 over V2 to the NR. It becomes V1 over V2 because of this negative sign there. So when we take it in, we're flipping that V1 and V2. Or if we remove that logarithm, what we have is T2 over T1 to CV equals to V1 over V2 to NR. We can further simplify it as T2 over T1 equals to V1 over V2 NR over CV. All right, and this equation is only true for reversible PV work, adiabatic, perfect gas. All right, yes.
Why did you use CV instead of CP?
Well, so in this case, we're talking about DU, right? So it's not me choosing CV, but because we're using DU, by definition, we have the CV defined as a partial derivative of U over T at constant V, while CP is defined as partial derivative of H over T at constant P. So it's not we choose to use it, it's because we're using the first law of thermodynamics, we're talking about the change of internal energy, and that's why we're using this equation. And becomes normal derivative because we're dealing with ideal gases. Any other questions? So thinking about what does it mean, right? So assuming we have a positive CV, what it tells us is if my final temperature is higher than my initial temperature, my final volume will be smaller than my initial volume, and vice versa. For a adiabatic, reversible PV work involving ideal gases. Okay. How are we doing so far? Feeling good? I mean, the math itself is not complicated at all. Like this is the level of calculus we're using, right? Just get familiar with using expressions of like CV, NR, U, and T instead of having a numeric answer. That's all. Yes.
How did you know that CV was a constant or not?
Oh, so this one we're talking about ideal gases. So for ideal gases, CV is a constant. Okay. With that in hand, let's move on to look at our summary. So this is the end of our chapter 2. We covered everything in chapter 2. Now, before we move on to chapter 3, we want to take this opportunity to quickly review what do we know. So in this case, this is going to be a summary of thermodynamic quantities, or in the other way to put it, like for example in here, for a question, we could ask you a combination of different keywords: reversible, adiabatic, perfect gas, etc. Right? So in this case, what we want to do is can we go over each of these terminologies and summarize what do we know, right? If I see a cyclic process, what does it mean in that problem? How do I translate the thermodynamic terminology like a cyclic process, isothermal processes, to something we can calculate, to something we can write out an expression from? So in this case, the first one, cyclic process. So the definition of the cyclic process tells us we have the same initial state and final state. effectively, what do we have is for any cyclic process, we have all the state functions does not change or remain constant, or the change of state function like internal energy, enthalpy, volume, temperature, pressure, they all equal to 0. All right, so these are all state functions. Right, so that's the forward thinking. Now let's take it from the backward thinking. Imagine we give you a random cyclic process. Upon derivation, we find out that this new function, a random function called smiley face, ends up the change of that smiley face for that random cyclic process equals to 0. Now we ask you, what do you know about the smiley face? Is it a state function or a line integral? So yeah, so in this case, right, so if that change vanished, then my smiley face is a state function. We'll use that in chapter 3 to define entropy, which is a new state function. And then we have reversible processes. So for this one, we have, remember the definition of the reversible process is saying the system is always infinitesimally close to equilibrium. Right now in this chapter, what we have covered is the infinitesimal change of reversible PV work equals to negative PdV. And notice that on top of PV work, we have other types of work that we care about. Say we can have electric work, right? So that's in electrochemistry. But for this class, we'll focus on PV work only. But later on, once you digested PV work, then the electrochemistry will become quite straightforward for you. So let's focus on PV work only. So this dW reversible equals to negative PdV. Now we have two different line integrals. We have work, we also have heat. So dW reversible equals to negative PdV. This is something we already learned. In our next lecture, we will talk about what does dQ reversible or reversible heat transfer, what does that mean? So that is equal to TdS that we will discuss later. All right. But for now, just focusing on dW reversible equals negative PdV. And then we have isothermal process. So get familiar with, say, isothermal, constant T, right? So that should be the link in our mind that we make. Now, in this case, what do we know? We know that for isothermal processes, if we have ideal gases, now my H is only depend on temperature. U is only depend on temperature. So for isothermal process, my delta T equals to 0, thus my delta H and delta U will equal to 0 for ideal gases. All right, so do not drop this assumption. Just make sure you know what we are referring to. All right, and then adiabatic process. What do we know about adiabatic process? Right, no heat exchange. So in general, whenever we see an adiabatic process, doesn't matter if it's ideal gas or not, it's always going to be Q equals to 0. And also dQ equals to 0. No heat exchange, whether it's infinitesimally small or not. And as a concluding note, we have isochoric and isobaric processes. Now, isochoric processes is when we have, if we only have PV work in the system, my volume is not changing, so my system is not doing work on the surrounding and vice versa. So if only PV work involved, then my total work equals to 0. And then for isobaric process, well, we didn't talk about isobaric process too often, but typically when you encounter isobaric processes, well, either you can take that pressure out from the integral since it's a constant, or what we know is about the physical meaning that my delta H equals to QP, right? So the physical meaning of enthalpy is the heat transfer at constant pressure. All right. So this is a quick summary in what we know. And let's see how do we use these summaries in solving problems, like very quickly. Now, this one will exist as an example question that's, well, try to answer one of these questions within like 5 minutes without doing any calculation, just using the intuition we gain and answer each sub-question in like 3 to 5 minutes. So for example, this question is asking us to decide whether or not my Q, W, delta U, and delta H, are they positive, 0, or negative? All right, so we're gonna do this together in a very quickly fashion. And I'll do it on the board so you have access to these questions together. So, question A. Let's read it together. What do we have? We're talking about a reversible melting of solid benzene at 1 atm and normal melting point. So in this case, it's giving us the melting is taking place at 1 atm and normal melting point. So we can translate that into constant temperature and constant pressure. And this is a reversible phase change. All right. And the question asks us about Q, W, delta U, and delta H. Now, since this one is melting of benzene, I need to give you one more piece of information. So the density of solid benzene is larger than the density of liquid benzene. And using our GenChem knowledge, we know the first thing is our Q melting, well, our delta H of the melting, or heat of fusion. This is gonna be a positive number. This is using our GenChem knowledge of knowing the process of melting absorbs heat. The top part will be given, and now we're trying to answer the question. So we know that the heat of fusion is gonna be a positive number. Or delta H melting is the delta H we're looking for this process, right? This is a constant pressure process. Remember, we talked about the physical meaning of enthalpy at constant pressure. We have delta H equals to QP. So my Q is also a positive value. All right. And then what about work? So work, well, it's reversible. So we have work equals to integral of negative PdV, taking the pressure out. We have the pressure times V final minus V initial. Now it is a melting, so we're talking about the volume of my liquid minus the volume of my mass, of my solid. And since the mass is the same, we have the density. Solid density is larger than the density of the liquid. So this one is a positive number. and hence we have this overall to be a negative work. But this one is going to be very small, since we're melting that liquid solid benzene. So the change of volume of that process of melting is going to be a very small value. This is going to be a small negative number. So we have delta H is positive, QP is positive. Now delta U equals to Q plus W. That's going to be also a positive number. All right, so without doing any calculation, just using our intuition to try to solve this problem. I hope we get the same answer. Okay, and now let's skip our part B, because this one is effectively the same one. The only difference is that the density of ice is lighter than the density of water, right? So one of them, the work is going to be different, but everything else is going to remain the same. So let's look at C. So C tells us we have a reversible adiabatic expansion of a perfect gas. All right, so quickly tell us what is the change of what is Q, W, delta U, and delta H? All right, so what is the Q for this process? Again, reversible adiabatic expansion of a perfect gas. Q is 0, right? And what about work? It's reversible adiabatic expansion. It's an expansion of the perfect gas. So W reversible equals to negative PEB. And since it's an expansion, our work is negative, right? System is doing work on the surrounding. And then we can use our first law of thermodynamics. So now this just tells you that's negative. I'm going to use that notation later on, like negative and then positive, etc. Now delta U equals to Q plus W, so that's also negative. And since we're looking at a perfect gas, so a perfect gas is only depend on temperature, right? So both my internal energy and enthalpy are only depend on temperature. So now my delta U is only depend on temperature. The delta U being a negative number tells us our temperature is dropping, so my delta H must also be negative. All right. You can also approach this problem by using the equation we derived. Remember, for this process, the reversible adiabatic process of an ideal gas, we derived that T2 over T1 equals to B1 over B2 NR over CV. Right, so you can get our results the same way. For example, we know it is an expansion, so my volume is going bigger, my temperature is dropping, right? So my temperature final is smaller than my temperature initial, and hence my delta U, delta H must be negative. And then you can go back to our work reversible, say that's also negative. So you can do it in both directions. You'll get the same answer. All right. Next one. We have here reversible isothermal expansion of a perfect gas. So how does this one work? Reversible isothermal expansion of a perfect gas. So what do we know? Again, reversible expansion. We have our system doing work on the surrounding. So work is negative. And we have isothermal expansion of perfect gas, right? So isothermal, the temperature is the same for perfect gases at same temperature, something is 0. Right, so the internal energy delta U is 0, delta H is 0. Now for this question, we now know work is negative, delta U equals to delta H equals to 0, so my Q must be a positive number. Right, so in the question, it can be a very quick short answer problem. Like say, now instead of telling you it's a reversible isothermal, I can say, hey, a reversible change of a perfect gas at 298 Kelvin. So we're giving you a specific temperature. That's the same as saying it is an isothermal process at that specific temperature. And you should be able to answer this question within like 2 minutes. You don't have to do any calculation, just using your intuition to solve this problem. All right, next up, let's see. We have adiabatic expansion of a perfect gas into vacuum. So this question, one of the things we know, well, adiabatic expansion, again, we have Q equals to 0. Now, the common misunderstanding we make is you too quickly to say this is a expansion, work must be negative. But in this case, what we have is expansion of the gas into vacuum. So it's not a reversible process. We cannot use our W equals to negative P dV anymore. Right, and also when expanding into the vacuum, my gas is not doing work on the surrounding. So this is the Joule experiment setup. We went over that. So for this process, we have Q equals to 0 because it's adiabatic. Delta U equals to 0. And W equals to 0 because it's expansion into vacuum. And my delta H must also equal to 0 because we have a perfect gas. So going back to the Joule experiment, I don't want to confuse you by this problem. So in the Joule experiment, we are taking the measurement of a random gas, right? So the Joule coefficient we defined is a partial derivative of temperature over volume at constant internal energy. So the Joule experiment is measuring the change of temperature with respect to volume at constant internal energy for any system of interest, not only for ideal gases. Now, think about it. For ideal gas, what is the Joule coefficient? Right, what we know about ideal gas, we know for ideal gases, my internal energy is only a function of temperature. So when my U is constant, my T is also constant. So for ideal gas, if we're doing the Joule experiment of an ideal gas, the Joule coefficient is effectively 0 for ideal gas. All right. What about the Joule-Thomson experiment? So mu JT equals to dt over dP at constant H. What is the Joule-Thomson experiment for ideal gas? That's also 0. Right, so these are special cases. So when we introduce the Joule experiment and Joule-Thomson experiment, again, we're trying to make a link between something we can measure, like temperature and volume, to something we cannot directly measure, like internal energy or enthalpy. But for ideal gas, which is a special case, we can derive the Joule coefficient and Joule-Thomson coefficient. Any questions? Okay. So let's move on to our last two parts. Reversible heating of a perfect gas at constant pressure. So reversible heating of a perfect gas at constant pressure. Actually, let me just not write it. It's straightforward enough. We can just think about it. So reversible heating. This tells us this is a heating of a perfect gas at constant P. So since we're heating it up, the temperature goes up. My delta U and delta H are positive. Right. So in this case, we're talking about the change at constant pressure. So my work reversible, since it's reversible heating, equals to negative V initial, V final, PdV. Now in here, we have pressure at constant. So taking pressure out, that's V final minus V initial. Let me make some space here. And by using our ideal gas law, PV equals to nRT, we know that pressure is a constant. Now V equals to nRT over P. So my temperature final is higher than my initial final. My volume final is also higher than my initial volume at constant pressure. So this inside is positive. And then this whole thing, the W reversible, is negative. And what about Q? Since my delta U equals to W plus Q, and we know that our delta U is positive, my work reversible is negative, my Q must be positive. So my system must be absorbing heat from the surrounding for this reversible heating of a perfect gas at constant P. All right, the same logic works for the last problem here. We have reversible cooling of a perfect gas at constant volume. Well, I guess similar logic. This one is actually more straightforward. So this is cooling. So we know that delta U and delta H are negative. We're talking about a process at constant volume. So my work is 0. And as a result, my Q must equals to delta U minus work to be a negative number. Yes.
So with these process of heating and cooling, we're saying that temperature is increasing and decreasing?
Right, so heating, by definition, is saying like we're heating it up, right? So the temperature, the initial temperature and final temperature are different. T final is larger than T initial. Okay, how do we feel about thermodynamics so far? This is chapter 2. And we so far discussed energy or internal energy, and we're linking internal energy with thermodynamic properties like temperature, pressure, and volume using heat capacities and Joule coefficient or Joule-Thomson coefficient. Now, in our next lecture, we will move on to chapter 3. So in chapter 3, we will look at the second law of thermodynamics. Remember, in our zeroth law of thermodynamics, we defined temperature, right? So the two objects of the same temperature, if they're in equilibrium, thermal equilibrium with a third object, they must have the same temperature. 1, 2, 3 must have the same temperature, right? So that's our zeroth law of thermodynamics. We got our state function, temperature. In our first law of thermodynamics, we got our state function, internal energy, at rest and no external field. In our chapter 3, we will define a new thermodynamic state function called entropy. And I'll see you on Wednesday.